Hey guys, welcome to the Exploring Quantum Optics Lab COVID-19 edition. This is the first video of what I envisage will be a 5 or 6 video series. So I'll try and cover all the kind of most essential points and give you guys some context for the manual. So you're going to read through the manual, but hopefully I'll go over all the critical details and you'll have an idea of what you're going to be doing, or what you would have been doing. You're still going to be doing data analysis. Data analysis is an important skill to have. And it is an experimental skill. So you still get to do that part. You're going to see me taking the data for you. So you're going to kind of feel like you would have known how to do it if you had done it. Okay, so this lab anyway, this is sort of a good lab to have during the pandemic because there's a lot of theory involved. The experiment's really easy to do, like in terms of actually taking the data. It's really quick. I hope you guys can hear me. I may not know if you can hear me until I've already done the video. I'm going to stop it now and then check, and then I'll edit it together afterwards. Alright. So that was pretty good. Well, it was alright. It was alright. I forgot what I was talking about before I stopped. But yeah, I think I was saying that there's a lot of theory involved because you need to understand a bit of optics and you need to understand quantum mechanics. And you haven't done any because you've sort of just started third year. You do both of those courses this year, but it's first semester, so I imagine you haven't done much, if any. So we got to kind of go over that, which is why there's lots of theoretical questions in the manual. So the idea is you would have spent some of the lab time in here doing that theory anyway. So you're still going to do that. So it kind of works out well. And the groups that have done this experiment, they only spent so far, only maybe an hour, or they spent a few hours, but they only really had to spend an hour or maybe 2 taking data. Okay, so yeah, it's quick to take data on this. It's not the most essential part. The most essential part is understanding the results that you're getting, understanding why we do the measurements that we do, and being able to analyze the results and see if that's what you expected or not. We just really want you to kind of understand quantum optics and how light behaves at a quantum level. That's essentially the point. And to understand, the statistical methods involved in the experiment. Okay, so first thing, I'll just show you a bit. So I'm just going to take this out of the... It's actually not a tripod. It's a boss head and clamp. So that's what it was attached to, which is not ideal. The glove is there so I don't destroy my phone screen by tightening it too much. So this is the experiment. So there's not much there. Let me try and hold this steady. Okay, so that's it. The manufacturers are Quantum Tools. They're a German company, and they make equipment not just for... This is, a tabletop sort of demonstrator. It's sort of meant for practical classes and educational purposes, but it does create a very strong, reliable entanglement quality of 2 photons. So it could be used for research, but they do also make research apparatus and components for observing quantum phenomena in an academic context. So yeah, they make good stuff essentially. Well, they say they do, but let's believe them for now. So what are we looking at? So you've got this white box. There's diagrams of this in the manual, so it might be good to just cross-reference with what I'm saying with the manual. This is the pump assembly. So there's a pump laser. I might actually just show you, I'll just show you. In general, I don't want students to be doing this, but I'm going to undo the white box is just a protective casing, so that doesn't really have to be here. But when we turn it on, it definitely does, because the pump laser is quite strong, and that can damage your eyes if you're not wearing the right protective equipment, which would be goggles that filter out the wavelength. So anyway, here's the pump assembly. So the box here is the pump laser, and that goes through a series of components. Maybe I'll change the angle a bit so you can see, like that. Okay. So the first component is an isolator, I believe, so it just stops light going back into the pump laser and potentially damaging it. And then you can see there's two mirrors on corners, 1, 2. I'm just putting my finger sort of over it, blocking it from view. That thing with the mark on it is an alignment laser. If you need to carry out some alignment, which I did before, students aren't expected to do that, but that's what it is for. It's for essentially lining up a beam. I'll explain it a bit when I've given you more context. The next component, where's my finger? Here it is. That one is a half wave plate, and that's for rotating the orientation of the electric field, or of the light, essentially the polarization direction. Hopefully you know what that means. If not, I am going to talk about it a little bit soon. So then the next thing you've got are 2 compensation plates. They're the last one and the one before the other one in the middle. The one in the middle is the barium BBO crystal. Forgot what it stands for. I've written it down in the manual. But that's essentially the nonlinear crystal where the down conversion happens. So for every pump photon that reaches that crystal at the right orientation, ensured by the wave plate, and with certain phase compensations, which is what these 2 components are. They're phase compensation crystals. So I write a little bit more about that in the manual. So yeah, the one in the middle is where the magic happens. Essentially, every pump photon down converts to 2 entangled spontaneous down conversion photons. So that's also sometimes called the down conversion crystal. And that's essentially the key component of this experiment. That's what gives us our entangled pairs. The entangled pairs come out, and we can see these, and maybe you can't see them very well, these markers. So the middle line is where the pump laser would be going, and then the entangled photons would come out at a very small angle to that. As you can see in the manual, they come out in like a cone shape. So those 2 come along, they reach the mirrors. So one hits the first mirror, the other photon hits this mirror, they come through the polarizers, and the polarizers, that's the only thing we actually tweak here. Like ideally, we may have to do some alignment, but we change the orientation of the polarizers, which lets through photons only of a certain polarization and blocks the rest. Or more accurately, lets through photons aligned with the polarization axis, which I read off from where that white line is. So now the polarization axis is 220 degrees from the vertical. So if it was 0, it would be aligned with the vertical. It lets through photons aligned with that axis all the time, and then as I move from that angle to an angle perpendicular to that, say 310 from 220, so I just added 90 degrees. I could have gone the other way too. I could have gone down to 130. Those photons will now never pass through here. If they were initially aligned, if they were aligned with the 220, they don't pass through when it's 310. And between there is a decreasing probability from 220 down to 310 of the photon passing through. Okay, so hopefully that made a little bit of sense. It's probably quite confusing. It sounded confusing when I said it, but we'll go through some of that theory because that's probably all quite new, so we'll talk about that, not to worry. So then each photon comes through its polarizer, which allows us to kind of manipulate which photons of which orientation we're letting through. So I guess what is more relevant is, like, say I set this one to 220, right? And this one to 220. Then I'm going to get photons that come through that have the same polarization. Okay, they're going to come through both ways. But if I set one to the orthogonal, 310, now I should ideally be getting no photons that have the same polarization in each arm. Anything that passed through here that was aligned with this one will not be aligned with this one. But then you've got all the polarizations in between that kind of have a more likely to pass through this one and less likely on this, or less likely on this and more likely on this. Anyway, we'll go through, but essentially all the experiments we're doing are based on these statistics, like how likely is it that a photon of such and such polarization, for example, something I often refer to as alpha degrees on this polarizer and beta degrees on this polarizer, as in, just some arbitrary linear polarization. What does linear polarization mean? We'll go through it. And then they're both coupled to this fiber optic cable. This one couples into here. This is just a lens, and it couples to the fiber optic, and this is another lens, couples to the fiber optic. The fiber optic cables come out and they go into these detectors here. Okay? And then I read out, it'll show me how many photons I'm detecting in a time interval on here. I don't want to turn it on just yet because I've taken the lid off and this video is going longer than I intended. They come into here and we read them out on the output. Sorry if my camera holding is very unstable. That must be kind of annoying. I've had quite a few coffees today, more than usual. What else? I think so. The other thing I might say is, these photons come out, as you can see in the manual, they come out in a cone. So they can either come out like this, or any rotation around the pump axis, so the pump light we know is in the middle. So this is not really a 2D, it is two-dimensional, but in reality they come out in a three-dimensional cone around that central pump laser. So like the pump laser is coming through at this height and at this translation, horizontally, it comes out there, and then the photons come out in a cone around that, right? And they're always opposite. So if a photon is up here, its entangled photon, its photon pair, like the photon that it's in a pair with, is down here, opposite the pump, okay? On the other side of the pump. So we can then change the angle of our mirrors and our fiber optic lens, and that's called changing the alignment. So then I'm picking up a different pair of photons ideally, and I can have the alignment set up so that I'm never going to get an entangled pair, like I'm picking up two adjacent parts of the cone rather than opposite sides. This is just a general example. Then I wouldn't have very good entanglement quality, right? I wouldn't be actually picking up entangled pairs in general. So this will behave not like an entangled pair. And an entangled pair is essentially only describable in a quantum way. It is a idealization of
a purely quantum system. You can't describe it using classical ideas and classical maths, and that's what we're going to kind of go through and work out for ourselves. So hopefully that'll make you believe that and not just have to take my word for it by the end of this lab. Okay, so that's the end of the first video. I'm going to get started on the second one, which is going to be more about the theory, going through some of the background. All right, cheers.